for a second. Okay, so we're just going to start with a little bit of the theory that will kind of help us get through the questions. The questions that you're asked both in the assignment and in this tutorial are kind of only a small amount of the full chapter. So I'm kind of just covering that here because the idea is these are like problem analysis sessions, but make sure you're familiar with everything you need to know for the exam. So kind of one of the basic things is this idea of black body radiation. And this is something we kind of saw before, but we're just getting into a little bit more detail, which is if you have a surface, it's going to be emitting some amount of energy. And the amount of energy it's emitting is that constant, the Stefan-Boltzmann constant to the 4. So it's purely based on temperature. And then just to relate this back to the stuff we worked on, if you have another surface that's surrounding it, you also have this transmitting at a back at the surface. And so often the kind of total Q that we talk about is our Stefan-Boltzmann constant, and then the T of our surface minus T of our surroundings. So, I mean, I think it's an important concept just that this difference in all of the other cases with convection and conduction, it's the temperature difference that drives it, that drives the heat flow. Rather with this, everything that has a temperature is just emitting radiation. And the balance comes from how much is it emitting versus how much is it receiving. So if it's emitting, it's emitting this much. This is the kind of root of the equation that we've seen before. But another important concept is that it's not emitting, it's emitting over a spectrum of different types of kind of radiation. And so it'll emit this over a whole waveform. And so that's kind of what this section is meant to represent. And what's important here is that depending on what we're interested in, we might care about only certain wavelengths. So in this class, for the most part, we're concerned mostly with this thermal radiation. And then for the and for solar radiation, we're looking at 0.3 to 3 nanometers. Sometimes you might be interested in your visible light, sometimes other things for different applications. But the way you know how much emissivity in a particular wavelength is with this equation. And this equation is fairly straightforward. It looks scary, but you have your wavelength, you have your temperature, and then you have these two constants, which are just numbers. So this is fairly easy to use. But the trick is we're often not looking for just solar radiation over at a single wavelength. We're looking at it over a range. So again, for solar radiation, 0.3 to 3. If you cared about microwave radiation, then you'd be looking at this range. And so in order to find the range, you need to integrate over, if this is your spectrum of emissivity, you need to integrate to find how much radiation is emitted in a range of wavelengths. And the way you do that is actually fairly practical. So this is the equation, which is, again, you're integrating to find your kind of range that you're looking for. But we don't actually use this equation. What we'll use instead is this table. And this table will tell us, rather than having to do the integration, this table will tell us what is our fraction, the difference between our lower bound wavelength or upper bound wavelength and our lower bound wavelength. That's the fraction of our total solar radiation that that is part of the wavelength we're interested in. And then our total radiation is, of course, that equation we talked about. So that's the general theory, but of course we'll do a example and I think it'll make more sense. That'll be the first question, and that's the first couple questions in your assignment. And then we're going to talk about solar radiation through a window. And in the question, essentially, we're going to deal with some costs and some total solar radiation. But essentially, the main theory part that we're going to use is this, which is our solar heat gain coefficient. And what this is the ratio of the solar heat gain through the window versus the solar heat gain instant to the window. So some amount of radiation comes in and some amount of it gets inside. And then some important concepts to, if you have a surface and you have instant radiation hitting it, then some amount of it's reflected, some amount of it's absorbed, and some amount of it's transmitted. And so what's transmitted is typically what's getting into the building. But you'll notice we don't use tau. We don't use this transmitted solar radiation. We use our solar heat gain coefficient. And a lot of the reason why we do that is just because windows are not a system, they're a little more complicated. So there's some amount transmitted, which is, again, mostly what we're interested in. But there's also some amount absorbed by the window. This amount absorbed will kind of heat up the window, and then some of that will then escape inwards. So this is kind of specific for windows. And it's something, I mean, you guys are in building engineering, so I'm sure you've seen this a ton. But this is why when we deal with windows, we get a little bit away from this kind of more pure theoretical stuff and a little bit more practical. Okay. So we'll go to question 1. So question 1, we have 3 millimeters thick glass window. It transmits 90% of the radiation. And so we have this range, our 0.3 to 3. So and it's essentially opaque from radiation of other wavelengths. So we know that, so what this is saying, opaque means not see-through. So there's some amount of radiation hitting it. It's basically nothing is getting through that's not within these two wavelengths, and 90% of what's between these two wavelengths is getting through. And so we want to determine the rate of radiation transmitted between 0 meters and 3 meters glass from a black body and at our two sources. So remember, our emissivity, or sorry, our solar radiation is coming from a source, so 58,000, that's temperature of the sun to start out with, and then we have another temperature. So the way we're going to go about solving this is we're essentially going to find our total emissivity, find out what fraction is between this wavelength, find, and then we're going to take 90% of that, and that's the amount that's actually getting inside. So we'll start, just calculate the area of the window, 9 meters squared, 3 meters by 3 meters. And then so our total emissivity from our source, 7 Boltzmann constant, T to the 4 times our area. And this is equal to 5.775 times 10 to the 8. Okay, so that's our total, and then we're going to find our fractions. So I'm just seeing a question on the chat. Tim gets conceptually why radiation isn't driven by temperature difference, but if TS equals T surroundings, then isn't Q rad 0. So yeah, it's true. In that case, what's happening is a body is actually just emitting the same amount that it's absorbing. So there still is heat transfer happening, but the net heat transfer is 0. So that Q radiation refers to the net heat transfer. So the distinction practically isn't always super important. I mean, temperature will go from hot to cold, but for some of the equations, it's good to kind of understand how that mechanism works. Okay. So for a fraction between 0.3 and 3, we're going to first find our wavelength T1. This will give us 1740 nanometers Kelvin. And I'm just going to go to the chart just this one time so we can kind of see what we're doing. Oh. So we'd be looking up that 1740. In this case, we'd have to interpolate. And so that thing we found is our nanometer times our Kelvin for this. From there, we can find our fraction. And then, of course, this is a 2-column chart. So when we run out here, we go over here. Oh. Sorry, guys, I'm having some pen troubles here. All right. Okay, so looking up on that table, we get 0.033. Okay, we'll do the same thing for this. 3 times our 5800 Kelvin. And this is 0.978. So now our fraction, oh, sorry, I shouldn't say equal. Okay, this is equal to 17,400, which leads. So our change in fraction is the difference between the two, which gives us 0.9453. So what that's saying is actually, in this case, most of our solar radiation from our source is in this kind of thermal range that's being transmitted. So our E that's transmitted is equal to our absorptivity. Sorry, our transmissivity. I'll actually write it out like this. Times our fraction, and then times our emissivity total, which is 0.9 times 0.9453. And then times, I'm sorry, it's this before, that's in watts. So 5.775 times 10 to the 8 watts. Okay, this equals 491, 300 kilowatts. So again, most of it is being transmitted. The total was 5, and we get kind of 4.9. Okay. So just in the interest of time, I'm going to skip part B, but part B is the same process, just with a different temperature. And with this case, maybe some will write down some of the key values. So our total emissivity is 491, 300 kilowatts. So much less to start with. But then interestingly, at this different temperature, the fraction of it that's within that solar range, or within that thermal range, was 0.27. So much less of the radiation coming off from this source is in this thermal range. So temperature does affect how much of the fraction is within the thermal range. And then in this case, our final power that was actually transmitted was 125.5 kilowatts, so much less. I mean, less for both reasons. Less because there's less to begin with, but also less of the thermal radiation is solar if it's a cooler body. Okay. Any questions about that? Okay, so if not, we'll move on. Okay, and this question is not super theoretically heavy, but kind of cool because it's very practical. And so we have this manufacturing facility. We know the glazing area, how much windows it are, and it has this double pane window with this solar heat gain coefficient of 0.7. So it's letting 0.7 of the heat in. And they're wondering whether or not it's worth it. If it's worth it to reduce our solar heat gain to this. Then they say the cooling season consists of June, July, August, September, and the heating season consists of October through April. The average daily solar fluxes incident to the west side in this latitude are all of these. So these are for the 12 months of the year. And then we know electricity cost and natural gas cost. And we're given the coefficient performance of the cooling system, 3.2, and the efficiency of the furnace, which is 0.9. Determine the net annual cost savings of coating the windows. So I think this question's cool just because it introduces this idea of, I mean, if you make a window kind of better against solar gains, it's good and bad. So it's good for the cooling season when you want the extra heat, and it's bad for the cooling season when you're trying to cool the space anyway. And so it's not always clear initially whether or not you'll save energy or you'll save money by making changes like this. And so this question, we're just going to calculate kind of if it's worth it. So I'll try to go through this pretty quickly. I won't be too repetitive. But basically, this is our summer. So we were given the months of our summer. And I should say per day, the average daily. So these are all our solar heat gains per day. And we are told that our summer, sorry, the cooling seasons, June, July, August, and September. So we're going to take our June, July, August, and September, 4.24 times how many days that are in that month. 6 times 31. And this is 482 kilowatts per year. Keeping in mind that this is specifically what's just due. This is the power that's just due to the solar. So this isn't like the energy use of the building. This is just how much energy entering the window through solar power. Or sorry, how much energy is hitting the window. We haven't gotten inside the window yet. Q winter, and I won't do the whole written thing, but if you did calculate it out, it'd be 615 kilowatt hours per year. Okay. So there's going to be some amount of increase in our summer load and some amount of decrease in our cooling load. Sorry, in our heating load. So start with the cooling. So RQ summer, our area of our glazing, and then we're specifically trying to find the decrease, not the total. So we're going to take a difference of our solar heat gain. This is without the film minus with the film. So this is our $42 kilowatts per year, 60 meters squared, 0.766 minus 0.3. And this is 12,031 kilowatt hours per year. All right. Okay. And then we're also going to look at the heating load increase. And same calculation again with the heating loads. And you'd get 5,000 or 15,350 kilowatt hours per year. And this is equal to, if you convert it, 523.7 therms per year. That's just because that's the way the heating is charged. Okay, so our decrease in cooling costs. Is that 12,000? Our electricity price. And then we divide it by our coefficient performance of our cooling system, which is $564 per year. And then decrease in heating costs is the 523.7 0.9 90 cents per therm. And then this one has a efficiency of 0.9. Yes, someone mentioned in the chat, Xavier, it's an increase. Thank you. And this gives us 524 per year. So you'll see right away that our heating and our cooling savings are pretty similar. So our cost savings is 564 minus 524. And that's equal to $40 per year. All right. And then in the question, they also asked, they gave us an installation cost of the film. So they do a quick payback period calculation. So the implementation is $15 per meter squared. $60 meters squared, which is $900. And our simple payback is equal to our implementation costs over our annual cost savings. $900 to install, $40 a year. So 22.5 years. So if you're running a factory and someone says they can save you $40 a month, $40 a year, sorry, it's not maybe the biggest sell. But I mean, this is one of the challenges we have working on buildings a lot of the time. What we do for cooling is bad for heating, or what we do for heating is bad for cooling, or what we do to save energy is bad for comfort. And so there is a lot to balance, and often massive savings are very difficult to find. Another thing that this doesn't really include, if it was a factory, you would have kind of ventilation fans, and you'd want to circulate that heat. So all the heat was coming in one side, and you wanted to actually take advantage of it, you'd want to mix it up. So there'd be some added cost there. So it may not even end up making a lot of money. And then, of course, it also depends heavily on how much you're paying for everything. So yeah, hopefully an interesting question to kind of get you thinking about that.